All right, let's just dive right into this explainer. We usually think of calculus as just a bunch of theoretical equations trapped in some heavy textbook, right? Something that only exists on a whiteboard. But today, we're going to look at how it actually translates directly into massive industrial engineering. It is literally the foundation of the physical world around us.
Take a look at this massive chemical plant. You see the towering columns glowing at sunset, the steam rising, that incredibly intricate piping connecting the whole shebang. It looks like a pure feat of physical labor and steel, right? Well, the secret is, this entire physical world is completely grounded in math. Every single pipe diameter, every column height, it all starts with calculus.
So here's our blueprint for today's explainer. We'll go from rates to real plants, see how we use derivatives to design reactors, look at powering separation processes with integrals, and finally, we'll apply differential equations in reality.
Kicking things off with Section 1, from rates to real plants, the overall journey.
Every massive industrial facility out there begins with a pretty straightforward three-step journey. Step 1, you've got to understand basic rates, like say how fast a chemical reaction naturally happens in a tiny beaker. Step 2 involves bringing in the complex math of calculus to accurately model and scale those rates up. And Step 3, taking those mathematical models and constructing the real plants. It's this direct pipeline from a chemist's observation on a microscopic scale all the way to an engineer's massive physical blueprint.
Moving right along to Section 2, designing the reactor using derivatives.
First up, we really need to understand the derivative. Now, fundamentally, a derivative just describes a rate of change on paper. It tells us exactly how one variable shifts in response to another at any given instant. So, if you're mixing chemicals, a derivative is going to tell you exactly how fast your product is forming right at this very second, taking into account things like temperature, pressure, and concentration.
Check out the direct comparison here. It's wild to see how an abstract mathematical rate literally governs physical scale. Think about it. If your derivative reveals a lightning-fast, super-violent reaction, your physical reactor might actually need to be pretty tiny but heavily reinforced with thick steel and aggressive cooling just to handle it. On the flip side, if the rate is super slow, you might need a massive, continuous tank. The derivative is literally dictating the actual safety specifications and the physical blueprint of the steel itself. All right, on to Section 3. Separation processes, powered by integrals.
We're shifting our focus now to the integral. Basically, an integral represents the accumulation of quantities over time or space. Instead of looking at an instant rate of change, like we did with the derivative, an integral adds everything up. It measures the total amount of a substance produced over, say, an 8-hour shift. Or it could be the total heat absorbed across the entire length of a 30-foot pipe.
And here's why that matters. The mathematics of accumulation is exactly what builds separation processes, like those huge towering distillation columns you see at chemical plants. Imagine slicing one of those massive towers into infinitesimally thin layers. Inside, you have liquids and gases interacting over and over again. Well, engineers use integrals that add up all of those tiny interactions, layer by layer, from the very bottom to the top. Meaning the actual physical height of a column standing against the sky, it's literally the physical result of an integral. Mind-blowing, right?
Which brings us to Section 4, equations in reality, differential equations.
Now, differential equations represent the complex relationship where those rates of change and those accumulations interact simultaneously. Because let's be real, in an actual industrial plant, things are not happening in perfect isolation. As chemicals react, temperatures rise, and as temperatures rise, the reaction rate changes. It's a loop. Differential equations allow engineers to dynamically model all of these constantly shifting, interacting systems.
So the really crucial takeaway here is that differential equations bring all of these interconnected elements together. The translation of rates, the physical sizing of the reactors, and the driving force of the separation columns, they bring it all together to dictate how the entire process runs in reality. If an operator opens a valve halfway across the facility, a differential equation is what predicts exactly how the pressure, the temperature, and the reaction rates will cascade and respond across the entire system. It's basically the grand conductor of the chemical symphony.
Looking back at this massive infrastructure again, you can probably appreciate it with fresh eyes now. The complex piping, the steam, the sheer massive scale of the operation. It isn't just arbitrary construction. It is simply calculus brought to life. It's the mathematics of change and accumulation, literally forged into steel, continuously running day and night.
So, I'll leave you with this final thought to ponder. The next time you drive past a massive industrial manufacturing plant, will you just see pipes and smoke?
Or will you be able to see the hidden calculus that actually powers the physical world around you? Because honestly, once you realize the math is there, it's impossible to unsee it. Thanks for diving into this explainer with me.